1.5, worst case efficiency of Quicksort. In this part, we will do worst case efficiency analysis. Actually, it is pretty easy. So let's look at the simple analysis. First, in order to get a worst case, we want to see under what special case the worst case happens. That happens based on our current experience. So we know when we distribute the data in a balanced way, we can avoid worst case. So the opposite, you can get the idea, the opposite, if the data is distributed in an extremely unbalanced way, then it should correspond to the worst case. Here, we try to look at that extreme case or cases. All right, so let's look at this diagram. In this diagram, you can see after we run one partition. So this is a situation after we run one partition. So you can see, other than the pivot element, we only have S region. The L region is empty. There is no element in the L region. That is an extremely unbalanced case, right? There is another one, similar situation, you can see, but this time we have all the elements except the pivot element all in the L region, and the S region is empty. These two cases will cause eventually the worst case. All right. So you can see it's pretty simple. In these two cases, you can see when we do the partition, we need to do n-1 comparisons. Compare with the pivot element. Both do the same n-1 comparisons. But still, these two cases have slight difference between them. So what's that? Which one is worse or equally bad? So if we compare a little more, we should also look at the swap operation. Right? The first one, if you look at the swap operation, when you do that, no swap operation, right? No swap operation. But the second one, you need to put the P in place. Because the first one, the pivot element already in place. You do not need to do anything. But the second one, you need to do one swap to put P in place. So that means one swap operation. That's the main difference. One difference in the swap operation. All right? Okay. Next, let us do some simple analysis. So we start with the recurrence relation for the worst case. It's pretty easy from the diagram. We can see it quickly. The running time complexity function T of n can be written in this way. T of n, you can treat it as the number of comparisons. T of n, the number of comparisons for sorting the whole array, T of n. Then after one partition, you get that extremal case, you just reduce the array size by 1. So you need to solve a problem with the size less than 1, n-1, not less than 1. So one less, one less than n, okay? T of n minus 1. That's the problem size you need to solve, all right? Then, when you do one partition, you need to do n minus 1 comparison. So you need to add to it. Yeah. So you get this recurrence relation, all right? Okay? So then, when you do iterations, you can get the total number of comparisons in this formula. So that is big theta of n squared. Big theta of n squared. Yeah. So that's pretty bad, right? Yeah. That is pretty bad. N squared. Yeah. Right. So you can see for the quicksort, it's worst case, still very bad. And you can also see the worst case corresponds to decreasing order or increasing order. Yeah. Two extreme cases. Increasing order, the array already sorted. Actually, it corresponds to the worst case, not the best case. Decreasing order also corresponds to the worst case, not the best case. Think about that. Yeah. All right. Next, I want to run a special example to let you see what happens during the multiple steps of partitioning. Yeah. It's pretty simple. Yeah. All right. Example for the worst case. Yeah. All right. When we start, we have an array in descending order. So we can call it's the L case because only L region, right? After the partition step, we have L region elements except the pivot element. Yeah. Then when we do another partition step, you can see we get S case, right? Yeah, S case. Yeah, because this red one is in place. We don't look at the element in place. It's already in place. Yeah. So we look at the remaining part. So you can see only S region is there. So it becomes S case. Yeah. Then alternatively, the next time, yeah, two elements in place, then the remaining elements L case. Right? You can see the pattern. Then L case, S case, then L case. All right? Yeah. So the last one, S case. Then you put all the elements in place. All right? Yeah. That is a special example for the worst case. You can see, yeah, what we are doing here. Basically, we switch from two different extremal cases, S case, L case, alternatively. All right, yeah, for this special example. All right, so this video, you get some idea about the worst case efficiency of the quicksort. Yeah. Next one, we will look at the best case efficiency, and that is our last video of part B. Yeah.